So we're going to continue talking about confidence intervals, working our way through the chapter on inference. And a confidence interval is really just a different way of using the information from our data to quantify how we express ourselves regarding uncertainty and making decisions. So when we talk about confidence intervals, we should also talk about confidence regions. And a confidence region is really the same thing as a confidence interval, except that it has more than one dimension. So there could be a situation where you have more than one parameter of interest, and you want to construct the values that contains both parameters with some specified level of confidence. And hopefully you remember what a confidence region or confidence interval is, but just in case you need a little brush up, a confidence region is a region that provides us with plausible values of our target parameters. And something is associated with a confidence region called a confidence level, and it tells us how likely that region or interval is to contain the target parameters under repeated independent trials. And so when we're talking about confidence intervals, we're not talking about the probability a specific interval contains a target parameter, but the probability that a set of intervals would contain the target parameter, where each confidence interval is constructed from an independent set of data. So I haven't posted this on Canvas. This is something that I use in some of my other introductory classes. And in this example, I'm just going to walk you through the code. But the idea is that we're going to take 100 samples from a population that has a standard normal distribution. And each sample is going to have a sample size of 10. And we're going to construct a confidence interval for the population mean, which we know in this case is actually 0. And if you look back at your notes from introductory mathematical statistics, your mathematical statistics class, then you'll know that you can use a t-interval to construct a confidence interval for the population mean in this particular setting, assuming that you don't know the population standard deviation, which we're not going to make that assumption here. And so what I'm going to do here is I'm going to create a matrix to store my samples in. I'm going to take 100 samples of size 10 and then store each one of those samples in my matrix. And then from each of those samples, I'm going to construct a t-interval. So that's what I'm doing right here. And now what I'm going to do is I'm actually going to plot my t-intervals. So each one of my t-intervals, so there's 100 of them in this case, and this vertical line, this vertical green line at 0, is the true population mean, and we want each of our confidence intervals to contain that target parameter. But we know that not all of our samples are going to be very good. And each time we obtain a sample, because of sampling variability, our interval is actually going to move around. Our sample standard deviation will be different, our sample mean will be different, and so these are going to shift left and right depending on what the measurements that the data actually contains. And what we want to see is that if we're constructing 95% confidence intervals, which we are in fact doing here, that 95 out of 100 intervals approximately should contain the true target parameter, which in this case is the mean and it's the value 0. And so I've highlighted in red here the intervals that do not contain the true value of the target parameter. In other words, these are the intervals that do not cross 0. You can see there's exactly 5 of them. That was simple luck on my part. It could have easily have been 92 or 98, but the more intervals that we construct, the closer the proportion should be to 95% of intervals that actually contain the true target parameter. And so that's the thing with confidence intervals. So under repeated trials, the proportion of intervals that contain the target parameter should match your confidence level. But it's not referring to a specific interval, because a specific interval will either contain the target parameter or it won't contain the target parameter. But when we look at the proportion of all intervals that contain the target parameter, it should be very close to our confidence level. And there's actually a direct link between confidence intervals and hypothesis tests. So if I give you a confidence interval at a 95% confidence level, then that's going to be matched up with a hypothesis test, a certain hypothesis test, having a significance level of alpha. And the idea is that if you reject your hypothesis test, those values, or any value that would cause you to reject your hypothesis test, would not be contained in your confidence interval. Any value that you fail to reject the null hypothesis for your hypothesis test would be in your confidence interval. Conversely, if we were looking at our confidence interval, any value in my confidence interval would cause us to fail to reject the null hypothesis if we were doing a hypothesis test, and any value outside our confidence interval would cause us to reject the null hypothesis if we tested that value in our alternative for the hypothesis, or in the null hypothesis, I should say. So confidence intervals, hypothesis tests, they really provide you with the exact same, or they use the information, but they portray uncertainty in slightly different ways. So whereas a significance test is going to provide you with a p-value, and we can make conclusions about whether or not the target parameter equals some value, a confidence interval doesn't provide a p-value. And so it's only going to be able to provide you information at a specific level of confidence. However, a confidence interval is going to provide you with values of the target parameter that are likely. When I do a hypothesis test, I simply know that I reject the null or I fail to reject the null. I don't know likely values of my target parameter. So a confidence interval provides us with likely values of our target parameter, which for a lot of people is actually preferable. So a lot of times people prefer confidence intervals or confidence regions to hypothesis tests because they like the additional information they gain in the form of plausible values of the target parameter. And in our context, one of the things that we need to think about when we're constructing confidence intervals is whether we want to construct confidence regions individually or simultaneously. And I'm not talking about the fact of should we construct more than one confidence interval or not. I'm talking about the fact of whether we should make a joint confidence statement. So can we construct a region that will simultaneously contain more than one parameter with some specified level of probability? And so we'll do an example of that later on in this section. So as we are constructing these confidence intervals for our hypothesis test, or as we're constructing these confidence intervals for our target parameters, there's actually a general form that they often take. So this is definitely not always the case, but for a lot of confidence intervals that people construct, it has the same sort of general form. It's an estimate of the target parameter plus or minus some number from a table, which we often call a critical value, and then some estimated value of the standard error. And as we'll see, our present context is going to match that as well. So if we wanted to construct confidence intervals for individual regression coefficients, then they take the following form. It's the estimated coefficient plus or minus the 1 minus alpha over 2 quantile of a t random variable with n minus p degrees of freedom, multiplied by the estimated standard error, which is given by this formula right here. So written in shorthand, I'm saying the same thing right here. So we already, when we're doing a hypothesis test for individual regression coefficients, we saw that we based our test on a t distribution. There's a link between that and the hypothesis test, though we're not going to derive it. But to construct this confidence interval, it's just the estimate plus or minus the appropriate number from our t distribution multiplied by the estimated standard error. And all of this information is pretty easy to obtain in R. If instead of doing constructing a confidence interval for a specific regression coefficient, we wanted to construct a simultaneous confidence region for all the regression coefficients, there's actually a special relationship that you can use using this sort of quadratic form. And this quadratic form is going to be less than or equal to p, which is the number of regression coefficients, including the target, including the intercept. So this is not just the coefficients for the predictors, but it includes the intercept as well. So we have this quadratic form is less than or equal to the number of regression coefficients multiplied by the estimated error variance multiplied by the 1 minus alpha quantile from this F distribution right here. And you can see that this isn't actually a formula. You couldn't use this formula like you could this one up here and to construct an exact interval. So this is a relationship between this quadratic form and these numbers over here. And so we actually have to use numerical methods to find what the actual confidence region is, which would be difficult for us to do by hand, but thankfully some nice people, some helpful people have actually programmed this up in R so that we can easily construct joint confidence regions for two regression coefficients at the same time, just using a simple function in R. And the package that we'll use to do that is the car package, though in fact there are other packages that you can use to construct these simultaneous confidence regions. So we have a formula for constructing individual confidence intervals. We have this relationship for constructing simultaneous confidence regions. Let's put those into practice in an example. So we're going to go back to the Galapagos data, and we're going to fit the model that has all the predictors in it. And we want to construct an individual confidence interval for the area coefficient, assuming that the other 4 regressors are in the model. So we fit our full model that has the predictor of interest and then any other predictors that are in the model. And then I'm going to use the summary function on my fitted linear model to obtain the information I need to construct the confidence interval. So since we want to construct a confidence interval for area, I would obtain the estimated coefficient for area. I could obtain the estimated standard error. And I can't use this t-value right here. That's a test statistic for a hypothesis test. I need to find the right quantile from my t-distribution. So we're constructing a 95% confidence interval, which means that 0.95 is equal to 1 minus alpha. So 1 minus alpha is my confidence level, and that is 95% in this case. And so solving for alpha, I see that alpha is equal to 0.05, and alpha over 2 is 0.025, which means that I want to find the 1 minus alpha minus 0.025 quantile, or 0.975 quantile of the t-distribution. And the degrees of freedom, n minus p, can be obtained using df.residual on your fitted model. So this will automatically extract it. So you don't have to manually try to figure out the sample size and the number of regression coefficients. So I think in this case it's 20, actually it says right here, n is equal to 30, p is equal to 6. So there's actually 24 degrees of freedom that we'll use. And so I obtain the 0.975 quantile from my t-distribution with 24 degrees of freedom, and I get 2.0639. And so now I'm just going to use those formulas that I saw a few slides ago to obtain the confidence interval for beta area. So I want my estimate plus or minus my t critical value multiplied by the estimated standard error. So in R, how I will do that is I'll take the estimate, and this is minus and plus the quantile from the t-distribution multiplied by the estimated standard error. And so my confidence interval runs from negative 0.07 up to 0.02. So that wasn't too difficult to do, but it seems like for something that would be so commonly obtained that somebody would make a way of easily obtaining that in R. And the answer is they have. So in fact, you can simply use, instead of doing that manually like we just did after fitting our model, you can actually use the conf_int function on your fitted model, and it will automatically construct 95% confidence intervals for each regression coefficient individually. So even though I have 6 confidence intervals here, these are not simultaneous confidence intervals that make some sort of joint statement about probability. So this is a 95% confidence interval for the intercept. This is a 95% confidence interval for the area coefficient. This is a 95% confidence interval for the elevation coefficient, etc. So these are individual 95% confidence intervals. And if you want to construct a confidence interval at a different level, then you actually just need to change the level argument. So we could change it to 0.98, for example. You can see these numbers change right here accordingly, but we'll just stick with the default of 0.95. So we'd have our same interval for the area coefficient, negative 0.07 up to 0.02. So let's answer some questions related to this information. So for what values of beta area would we fail to conclude the alternative hypothesis in a two-tail test for beta area using alpha equal to 0.05? And then another question, do we believe that beta area is different from 0? So once you pause this video for a couple minutes, think about this, write your own answer, and then we'll look at the solution together as a class. Okay, well I hope that was a useful little thought exercise for you. So for this first question, we want to know the values of beta area that would cause us to fail to conclude the alternative hypothesis in a two-sided test using alpha equal to 0.05. So let me just be very clear here. So we're doing a test with alpha equals 0.05. This is a hypothesis test for beta area.
So alpha is equal to 0.05, and my null hypothesis is that beta area equals C versus the alternative hypothesis that beta area is not equal to C, where C is just some number that we're choosing. And typically we choose C to equal 0, but in this case we want to know the values of beta area that would cause us to fail to conclude the alternative hypothesis. And so another way of saying this question is for what values of C would we fail to reject the null hypothesis? Okay, so that's my question. And as I mentioned, there's a relationship between this two-sided hypothesis test and our two-sided confidence interval. So our two-sided confidence interval for beta area ran from, and I have the values right here, so I'm just going to copy and paste those over. So negative 0.07 up to 0.02. And for what values of C would we fail to reject the null hypothesis? And it would be for C in this interval right here. So any values that are in our confidence interval, those are the values of C that would cause us to fail to reject our null hypothesis here. And this should actually make intuitive sense. So we think that we've stated that a confidence interval is a set of plausible values for our target parameter. So in other words, these are values of our parameter that we think are reasonable. If I think a value of my parameter is a reasonable value, then why would I reject the null hypothesis that the parameter equaled that number? That wouldn't make any sense. And so for any value that's in our confidence interval, that would cause us to fail to reject the null hypothesis if we were doing a test that coefficient equaled a value inside the confidence interval versus the alternative that it was not equal to the value that was inside the confidence interval. Conversely, if C was any number outside this interval, then we would conclude the alternative hypothesis for this particular test. So, looking at that, do we believe beta area is different from 0? Well, 0 is in our confidence interval, right? We've already stated that any value that was in our confidence interval would cause us to fail to reject the null hypothesis in this test. And so we do not think that beta area is different from 0. So no, we do not think beta area is different from 0 because 0 is in my 95% confidence interval for beta area. So hopefully that makes sense. If not, then definitely let me know so we can clarify that in class. Let's move on to joint confidence intervals. So as I mentioned before, we have the situation where we have more than one parameter, target parameter of interest, and sometimes we want to make confidence statements about both of them simultaneously. So when we're constructing a joint confidence interval or a joint confidence region, we're stating that the values of both parameters simultaneously are going to be in that confidence region with a specified level of confidence. So we want to construct joint confidence intervals for, and this is actually off, it says beta DPI and beta pop 75, that's not correct. It should be beta area and beta adjacent. So I will adjust that in my future lecture slides, sorry about that. So this should be beta area, this should be beta adjacent here. And what we do is we load that car package, then we're going to use the confidence ellipse function. And the confidence ellipse function is going to take your fitted linear model, and then you have to specify which coefficients you want to construct the confidence ellipse for. Then I've also specified limits for the y-axis in this case to make sure that I could show the origin and all values of the confidence ellipse. So let's actually just look at the R code here. So I have my fitted linear model, so let's just take a look at that. Okay, and you can see here that the area coefficient is in the second position of this list, so 2, and then we also wanted the regression coefficient for adjacent, which is 3, 4, 5 in the 6th position. Okay, so that's the reason why I'm choosing 2 and 6 here, because the area coefficient is in the second position, and the adjacent coefficient is in the 6th position. Or if you wanted to use the summary function, that might even be easier to see. We just count how many rows down in this table we need to go to find the 2 coefficients. So area is in the 2nd row, and adjacent is in the 6th row, which means that to construct a joint confidence region for the area and ellipse coefficients, or area and adjacent coefficients, we need the information in the 2nd and 6th positions of our fitted linear model. So I run that function, so I need to load the car package. I haven't done that yet. So I load the car package and I run the confidence ellipse function, and there is my joint confidence region. So this is the center point of my confidence region. If you actually compare this to the estimated values of area and adjacent, you'll see that this is just the estimated values of each. And then we use that inequality given right here to derive what the ellipse should be, what the relationship is between those 2 parameters and that inequality. So after I do that, I'm going to add the origin to the plot. So I'm going to use the points function. I'm going to add the point 0, 0, which is up here, and that's the reason why I actually extended the y-axis to include the value 0. And what I'm going to do here is I'm actually going to put vertical lines that correspond to the individual confidence interval for the area coefficient, and horizontal lines that correspond to the individual confidence interval for the adjacent coefficient. Okay, so this is the individual confidence interval, 95% confidence interval for area. This is the individual 95% confidence interval for adjacent. And you can see that there's a lot of overlap between the individual confidence intervals and the simultaneous confidence region, but they don't match up perfectly. And that's because our regression coefficients, I should say our regression coefficients, our estimated regression coefficients and our predictors are actually correlated with each other. And so that should be taken into account when we are constructing our confidence region, which is what this particular method does. So now that we have constructed that confidence region for area and adjacent, we can ask a question here. So do we believe that beta area is equal to beta adjacent equals 0, and why? So why don't you take a second, pause this video, think about that, looking at this plot, and then we will come back together and look at the solution as a class. Well, I hope that was helpful for you. So what are we going to do here? So we're going to think about what we did before, where we looked at our confidence region, and we thought about how this would translate to a hypothesis test. So for any value in our confidence region, it would cause us to fail to reject the null hypothesis for those particular parameter values of beta area and beta adjacent. So just to be very clear here, our null hypothesis is that beta area equals, I guess, C1, and beta adjacent equals C2. And we really should have, given that the other parameters are in the model, or other predictors in the model, right? Because this has a context. We don't normally state that. And then our alternative hypothesis is at least 1 is not equal. So our null hypothesis is that both area and adjacent equal some specific values. The alternative is that at least one of them is not equal to those parameter values. And the question that we're asking is, what's the conclusion when C1 equals 0 and C2 equals 0? So do we think that area and adjacent are different from 0? At least one of them is different from 0. And looking at our joint confidence region in this graphic right here, we can see that the point 0, 0 is not found in our confidence region, which means that we would reject the null hypothesis that both values equaled 0 simultaneously. So once again, because 0, 0 is outside of our confidence ellipse, we would reject the null hypothesis that both regression parameters equal 0. So our conclusion here to this question is, yes, we believe they're different from 0 because, so we believe that beta area or beta adjacent is different from 0 because the point 0, 0 is outside of our confidence region for beta area and beta adjacent. And in fact, in this case, looking at this graph, it seems pretty clear that both of them are in fact different from 0, because it's not just that the coefficient for area doesn't, or that we don't include 0 on the horizontal axis, or we don't include 0 on the vertical axis, but we don't include 0 on either axis in our confidence ellipse. And so this makes us think that in fact area coefficient and area, or beta area and beta adjacent, are both different from 0. So just a few other things I want to point out about this confidence ellipse. So you notice that in terms of height and width, our joint confidence region is wider and taller than the individual confidence intervals for beta area and beta adjacent. And that actually makes sense because we're only making individual statements for each of these individual confidence regions. So we're only making a statement about beta area here. We're only making a statement about beta adjacent here. And if we want to make a simultaneous statement about both parameters at the same time, then we need to include more area, essentially, to make sure that our confidence level is matches up with what we're stating. However, surprisingly, the overall area of the joint region is smaller than the area of the intersection between the two individual confidence regions. Okay, that's because we have this sort of this sideways or this angled ellipse. And the reason that it's angled, as I mentioned before, is because the estimated regression parameters are positively correlated. They're correlated, and so we take that into account when we're constructing our confidence region. And if the lines of the individual confidence regions were tangential to, so that means it would just intersect at this one point right here at the end here, and then the horizontal direction would be right here and right here. So if our individual confidence regions were tangential to the confidence ellipse here, then in that case, the individual confidence regions would also satisfy the joint confidence statement. But that's hopefully straightforward to see, because if our joint confidence level for this is 95% and our individual confidence region include the entire joint confidence region plus a little bit extra, then the joint confidence level of our individual confidence regions would have to be at least 95%, because it includes everything that's included in the joint confidence region. And you can get some interesting relationships when you are constructing these joint confidence regions, just because the individual confidence regions don't really take into account the correlation between the estimated regression parameters. So you can have situations where the individual confidence regions or confidence intervals would cause us to fail to reject a null if we just looked at the information in them, but the joint confidence region would cause us to conclude the alternative. It's possible that the origin could lie outside the individual confidence intervals but inside the ellipse. You can draw pictures where this is definitely the case. So you have to be careful. So just because you would make certain conclusions using the individual confidence intervals does not mean that you would make the same conclusions using the joint confidence intervals. And if you have more than one parameter, then you really want the joint confidence intervals or the confidence regions when you are making your conclusions and making your interpretation. So make sure that you're using the right tool for the job.